Welcome to The Explainer. So today, we're cracking open one of the greatest scientific detective stories ever told. It's this decades-long, totally mind-bending quest to figure out what an atom really is.
I mean, it sounds like a simple question, right? But the answer is shocking. For, most of history, we just assumed matter was solid, simple, straightforward. But as you're about to see, a whole series of stunning discoveries blew that idea apart, revealing this hidden universe that's stranger and way more powerful than anyone ever imagined. All right, so our story really kicks off with an idea that stuck around for over 2,000 years. This picture of the atom as just a tiny, unbreakable, solid little ball.
Yeah, for literally millennia, the atom was it, the smallest possible thing, the fundamental building block. But then, in 1897, a physicist named J.J. Thomson was messing around with these things called cathode rays, basically just zapping electricity through a vacuum tube, and he found something incredible. He discovered a particle that was thousands of times smaller than an atom, the electron. And just like that, the atom wasn't indestructible anymore. It had smaller parts inside.
So if the atom could be broken apart, what did it look like inside? Well, Thomson came up with what we now call the plum pudding model. Just picture a big, round blob of positive pudding, and then scattered all through it are these little negative electrons, kind of like plums or raisins. All the charges balanced out, so the atom was neutral. It was a pretty clever idea, but it was about to get a serious reality check.
Now, think about it. If the atom really is this soft, spongy pudding, then shooting tiny particles through it should be, well, pretty boring. A physicist named Ernest Rutherford decided to put that to the test, and in doing so, he set up one of the most important experiments in the history of science.
Okay, so here's what his team did, and it was actually brilliant in its simplicity. They took a stream of tiny, positively charged alpha particles. Think of them like microscopic cannonballs. And they fired them at a sheet of gold foil that was hammered so thin it was just a few atoms thick. All they wanted to do was see what happened when these little cannonballs went through the pudding of the gold atoms. And this is where things get absolutely wild. The expectation, the alpha particles should have just blasted right through, like shooting a BB gun through a cloud of mist. And yeah, most of them did, but some of them got knocked way off course. And get this, about 1 in 8,000 of them bounced almost straight back. That just shouldn't have happened. It was impossible. Rutherford himself was completely stunned. He later said it was as incredible as if you'd fired a 15-inch cannonball at a piece of tissue paper, and it came back and hit you. There was only one possible explanation. The atom's positive charge and all its mass weren't spread out at all. They had to be crammed into an unbelievably tiny, dense point at the center. He called it the nucleus. The atom, it turned out, was mostly empty space.
So Rutherford came up with a whole new model for the atom. And it perfectly solved the mystery of the gold foil experiment, but, oh boy, it created an even bigger problem. A paradox so huge it threatened to break physics itself.
This was the new picture, a tiny, heavy, positive sun, the nucleus, with these light, negative electrons orbiting it like little planets. This solar system model totally explained why most of the alpha particles flew through empty space and why a few ricocheted off that dense center. But there was a catastrophic flaw.
You see, according to the laws of physics they knew back then, any charged particle moving in a circle is accelerating, and an accelerating charge has to give off energy, like a tiny little radio tower. This would mean the electron should be constantly losing energy, causing it to spiral faster and faster into the nucleus until it crashed. The whole process would take less than a trillionth of a second. Every atom in the universe should instantly self-destruct.
But they don't, right? I mean, look around. The chair you're on, the air you're breathing, it's all still here. You're still here. So Rutherford's model had to be right about the nucleus, but it couldn't explain why anything exists at all. The rulebook of physics was broken, and it was going to take a leap into a very strange new reality to fix it.
Okay, so physics is in crisis. Enter our next detective on the case, the Danish physicist Niels Bohr.
Bohr took a look at the problem and had this incredibly radical thought. He basically said, what if the problem isn't the model? What if it's the rules? What if, on the tiny scale of an atom, the normal laws of physics just don't apply? It was time to use the weird new rules of quantum mechanics.
And this is just a brilliant way to picture his idea. In our everyday world, energy is like a ramp. You can have any amount of it, you can be at any height. But Bohr said that in an atom, energy is like a staircase. An electron can only exist on specific steps, or energy levels. It can be on step 1 or on step 2, but it can never, ever be floating in between. And here is the genius part. As long as an electron stays on one of those energy steps, it's perfectly stable. It doesn't radiate away energy and the atom doesn't collapse. Problem solved. It only gives off energy as a little packet of light called a photon when it physically jumps down from a higher step to a lower one. And not only did this save the atom, it also perfectly explains something else. You know how different elements glow with specific signature colors? That's the light from these exact electron jumps.
So, with the electron mystery solved, scientists could finally turn their attention back to that tiny, dense nucleus at the heart of the atom. And what they were about to find locked inside, well, it was a source of power on a scale that nobody had ever dreamed of.
Okay, this is a little mind-bending, but stick with me. If you take all the protons and neutrons in a nucleus and weigh them individually, their total mass is always a little bit more than the mass of the final nucleus, all stuck together. So where did that tiny bit of missing mass go? It was converted directly into a tremendous amount of energy, the binding energy, that holds that nucleus together, all thanks to Einstein's famous equation, E equals mc squared.
Now, it turns out that some nuclei are way more stable than others. The sweet spot, the most stable elements are right in the middle of the periodic table, with things like iron. And this means you've basically got two paths to releasing that incredible binding energy. Either you split a really heavy nucleus apart, or you smash two really light ones together.
And these are the two processes that literally changed the world. You got fission, where you take a big, heavy, unstable element like uranium and break it apart into smaller, more stable pieces, releasing a ton of energy. And then you've got fusion, where you go the other way. You take light elements like hydrogen and force them together to make a heavier, more stable element, which releases even more energy.
Just how much energy are we talking about here? Well, that number, 26.7 mega-electron-volts, is the energy that gets released every single time four hydrogen atoms fuse together to become one helium atom inside our sun. It's a reaction that is millions of times more powerful than any chemical reaction, like burning something. It is literally the engine that has powered our entire solar system for billions of years.
So, in the end, this whole incredible detective story, this journey that took us from a solid little ball to a quantum solar system, did way more than just satisfy our curiosity. It unlocked the fundamental forces of the universe. It gave us access to the engine that drives the stars themselves.
And really, isn't that what's so beautiful about science? Every time you solve a mystery, every time you crack a code, you just open a door to an even bigger, more fascinating question. The investigation, it never really ends.